Flow through an annulus. In this part, we'll see flow of a liquid through an annulus between two coaxial cylinders. The liquid flows in upward direction under the influence of a pressure difference and gravity in an annular region between two coaxial cylinders of radii kappa r and r. So it is flowing in upward direction. Let the length of the cylinders be L. Assumptions: steady state flow, laminar flow of fluid, fluid of constant density ρ and viscosity μ. We will develop equation for flux profile, velocity profile, average velocity, maximum velocity, mass flow rate and drag force on tube. We are selecting cylindrical coordinates to derive the equations, that is r, theta and z direction. Here, velocity is only in z direction. In r and theta direction, velocity is 0, that is Vr is equal to V theta, which is equal to 0. The only non-vanishing velocity is Vz, and Vz is changing only with r. That is Vz profile is changing with r, it is not depending on theta or not changing with z. There are two methods to get velocity profile and flux profile. First is simplified method, second is equation of motion. Shell momentum balances. Rate of momentum in by convective transport minus rate of momentum out by convective transport plus rate of momentum in by molecular transport minus rate of momentum out by molecular transport plus force of gravity acting on system is equal to 0. This is the general equation for shell momentum balance. Now the simplified method or generalized method, select the coordinate system and origin. We selected the cylindrical coordinate system and origin. We are selecting origin at the bottom of the cylinder. We have three choices. We could have chosen at top or the middle or at the bottom. We'll proceed with the bottom. Write a momentum balance. Let the thickness of the shell approach 0 and make use of the definition of the first derivative to obtain the corresponding differential equation for the momentum flux. Integrate this equation to get the momentum flux distribution. Insert Newton's law of viscosity and obtain a differential equation for the velocity. Integrate this equation and use appropriate boundary conditions to get the velocity distribution. Use the velocity distribution to get other quantities such as the maximum velocity, average velocity, or force on solid surfaces. Total momentum flux phi ij is equal to P delta ij plus tau ij, that is molecular flux, plus rho vi vj, that is convective flux. Here P delta ij is the component of force acting perpendicularly to a surface. All components in r direction and theta direction will be 0 because Vr is equal to V theta, which is equal to 0, and corresponding delta ij's is equal to 0. Therefore, flux will only remain in z direction and its components will be phi rz, phi theta z and phi zz. Checking from the conditions of the problems, we use this equation and Newton's law of viscosity. Tau ij is equal to minus mu dou vi dou xj plus dou vj upon dou xi 2 by 3 mu minus kappa into 1 upon r dou r vr upon dou r plus 1 upon r dou v theta upon dou theta plus dou vz upon dou z into delta ij. Using all these four equations, we simplify and substitute to get phi rz is equal to tau rz plus rho vr vz, which is equal to minus mu dou vz upon dou r plus rho vr vz, and phi zz is equal to p plus tau zz plus rho vz vz, which is equal to p minus 2 times mu dou vz upon dou z plus rho vz vz. Now as we can see from this diagram, the velocity distribution will not be same at all points in this z direction, as it is function of r. At some point there will be maximum velocity, that is it will be lesser at the inner region, then it will increase, and at some point it will reach maximum, and then it will again decrease. That is the velocity distribution. So we'll assume at some lambda r, the Vz is equal to Vz max, and this plane where Vz is Vz max, there will be no momentum flux. That is, this is the surface of no momentum flux. Then we have shear stress or momentum flux distribution. Because of their nature, it will go from negative to 0 to positive as we go outwards. Therefore, the rate of z momentum in across annular surface at z equal to 0 will be given by 2 pi r delta r to phi zz at z equal to 0. Similarly, out will be at z equal to L, as we are taking origin at bottom, z equal to 0, z equal to L. In across cylindrical surface equal to 2 pi rl phi rz at r. Rate of z momentum out across cylindrical surface at r plus delta r, 2 pi rl phi rz at r plus delta r. And gravity force is acting downwards on cylindrical shell, 2 pi r delta r L rho g. Using those equations, we can write the shell momentum balance as 2 pi rl phi rz at r minus 2 pi rl phi rz at r plus delta r plus 2 pi r delta r phi zz at z equal to 0 minus 2 pi r delta r phi zz at z equal to L plus 2 pi r delta r L rho g is equal to 0. Now, rearranging and applying limits, it gives limit delta r tending to 0, r phi rz r plus delta r minus r phi rz at r upon delta r is equal to phi zz at z equal to 0 minus phi zz at z equal to L upon L plus rho g into r, which gives dou by dou r of r phi rz is equal to phi zz at z equal to 0 minus phi zz at z equal to L upon L plus rho g into r, which implies d by dr of r tau rz is equal to p naught minus rho g of 0 minus pl plus rho g L upon L into r. Here p naught and rho gh are the pressures. We can write this in combined as p naught minus pl upon L into r. Tau rz is equal to p naught minus pl upon 2L into r plus c1 upon r after integrating this equation. Next, we will apply the boundary conditions. There are 4 types of boundary conditions. No slip condition for solid fluid interfaces plane, modified no slip condition for liquid-liquid interfacial plane, zero flux condition for liquid gas interfacial plane, and logical boundary condition. We will be using no slip condition. From this equation we can write minus mu dvz upon dr is equal to p naught minus pl upon 2L into r plus c1 upon r. Upon solving and integrating, it gives Vz is equal to minus of p naught minus pl upon 4 mu L into r square minus c1 upon mu into ln r plus c2. This is our equation 2. Using no slip condition at r equal to r and r equal to kappa r, at both places Vz is equal to 0, like we saw with the diagram, velocity distribution. Second equation implies 0 is equal to minus p naught minus pl upon 4 mu L into r square minus c1 upon mu ln r plus c2. 0 is equal to minus p naught minus pl upon 4 mu L mu kappa square r square minus c1 upon mu ln kappa r plus c2. Subtracting eliminates c2. Subtracting this equation, solving for c1, we get C1 is equal to P naught minus PL into R square upon 4L into 1 minus kappa square upon Ln 1 minus kappa. Substituting this C1 back into equation 2 gives C2. C2 is equal to P naught minus PL upon 4 mu L R square 1 minus kappa square upon Ln 1 upon kappa Ln R. We have now both the constants C1 and C2. So we put this in equation 2. Finally, when we put this to equation 2, we get Vz is equal to minus P naught minus PL upon 4 mu L into R square minus Ln R upon mu into P naught minus PL upon 4L R square 1 minus kappa square upon Ln 1 upon kappa plus P naught minus PL upon 4 mu L R square into 1 minus kappa square upon Ln 1 upon kappa into Ln R. So the final equation that we get for velocity is Vz is equal to P naught minus PL upon 4 mu L R square into 1 upon R square plus 1 minus kappa square upon Ln 1 upon kappa Ln R upon R. We can find maximum velocity and average velocity. So assume maximum velocity as is at R equal to lambda R. When Vz is equal to Vmax, we have surface of zero flux. Therefore, tau Rz is equal to 0. Using these two conditions, we can write Vz max is equal to P naught minus PL upon 4 mu L R square into 1 minus lambda square plus 1 minus kappa square upon Ln 1 upon kappa Ln lambda, and tau Rz is equal to P naught minus PL upon 2L R into R upon R minus 1 minus kappa square upon 2L 1 upon kappa into R upon R. This is 0. So it gives 2 lambda square is equal to 1 minus kappa square upon Ln 1 upon kappa. From 3 and 4 we get Vz max is equal to P naught minus PL upon 4 mu L R square into 1 minus lambda square into 1 minus Ln lambda square. For average velocity, we integrate it in the limits of R, kappa R to R and theta 0 to 2 pi. So we get integration of 0 to 2 pi integration of kappa R to R Vz R dr d theta upon 0 to 2 pi kappa R to R dr d theta. Vz is equal to P naught minus PL upon 8 mu L into R square into 1 minus kappa to the power 4 upon 1 minus kappa square minus 1 minus kappa square upon Ln 1 upon kappa. So this is the average velocity. For mass flow rate, we have the equation W is equal to pi R square 1 minus kappa square rho into average velocity, which gives W is equal to pi P naught minus PL R to the power 4 rho upon 8 mu L into 1 minus kappa to the power 4 minus 1 minus kappa square upon Ln 1 upon kappa. Drag force on wall Vz is equal to 2 pi kappa RL into minus tau Rz R equal to kappa R plus 2 pi RL into plus tau Rz R equal to R, which is equal to pi R square 1 minus kappa square P naught minus PL. Limitation. These equations are only valid for laminar flow and Reynolds number equal to 2000. Reynolds number in general for annular region is given by R is equal to 2R1 minus kappa into Vz average rho upon mu.
Okay, so here we give as an a problem regarding to annular region with the inner cylinder moving axially annular of flow. This question is taken from the actually this question is taken from the bird's book. So let's see the question. A cylindrical rod of a radius r moves axially with velocity vf is equal to v along the axis of the cylindrical cavity radius r, as seen in the figure. Yes, we have seen. Pressure at both end of the cavity is the same. So the pressure of the end of the cavity is same. So that a fluid motion through the annular region slowly because of the road motion. Okay, so what is given in the question here, that the uh, pressure along with the velocity v, the axis of a cylindrical cavity as radius are we are showing in both of the end. The pressure at both end of the cavity is same. Actually the pressure of the cavity of the both end is same. So that what will be to happen, that annular region of the slowly it will move toward the road of the motion. Okay, so let's see the here are the some questions like find the velocity distribution of the narrow angular region, find the mass rate flow through the annular region, obtain the viscous force acting on the road over the length L, show that the result in C as written in the plane slits and multiplied as the curvature friction. Problem of the kinds arise studying performance for wire coating lines. So this is the diagram in which we are shown here like cylinder of radius r. Okay, so this is the cylinder of the inside radius and rod of the radius. This is the between of the radius of with which we are moving with velocity v, and this is the fluid at a pressure P naught and is a fluid at a pressure P naught, as the cavity is the same from the both side. So let's move to the solutions. So this is the solution from the equation of the motion, as it is the given as a f is a flux vector, so v into f is equal to 0, and by the no end effects it will be cancelled simply, and then since the steady states and no end effect, simply it will get cancelled and we will get only this expansion of the continuity. What is the expansion of the continuity? Firstly see here like firstly see here, or the pressure is equal to constants and v r is equal to v d is equal to 0. So this simply get cancelled and this we get equation of the motion of z component. So this is the steady states and the parallel. Due to this all the this get the cancelled and only we only get this equation. Okay, so now the Goveri, what I will say, equation and the boundary condition. So d by dr r into dy is simply equation is given, boundary condition 1, boundary condition 2. So this is the boundary condition 1 and this is the boundary condition 2. In this at r is equal to r is given as an this, and at r is equal to r at boundary condition 2 and boundary condition 1. So for velocity distribution, integrated view dvr upon dr, so cr, in which we have just integrated this and we get this one, this we get by applying the boundary condition c1 is equal to ln k and c2, then we will apply the boundary condition and this we will get, then the velocity of the distribution, this we will get. Now what will be the shear stress distribution? Okay, so this will be the our shear stress distribution. Okay, so this is the shear stress distribution. Now, moving forward, what will be the mass flow? What will be the mass flow velocity distribution? So this is the mass flow velocity distribution in which W is equal to rho 0 to 2 pi into VR into dr and pi r square PV by 2 into 1 upon ln k. Drag force, as we all know what is the drag force formula, Fd is equal to 2 pi RL, okay, and then 2 pi ln V upon ln into 1 by x. Now we need to just show the result of the C that has been taken as a curvature correction. Since this is a Taylor series, so we need to just see as a Taylor series only. So this is the Taylor series form. In this we will form this and we will get the equation. So this we will get as an equations. So thank you everyone.